Next is about Poisson's ratio. The Poisson's ratio may be a little confusing for beginners. Imagine that you are pulling a bar. Then, can you imagine the bar becomes thinner? It should not be so surprising. It would be easier if we could explain this is because the volume is constant. But in general, when a bar is pulled, the volume increases slightly. Strictly speaking, the assumption that the volume of material is constant causes some inconveniences. So, we need to define horizontal strain rate when a bar is stretched vertically. We are considering a general situation shown in this illustration. Imagine that we are pulling a round bar at a load P along the longitudinal direction. Now, the load is acting only along the longitudinal direction of the bar. No load is acting on the other surfaces, which means no load is acting in the vertical direction. We assume that the length of the bar has changed from L0 to L, while the diameter of the bar changes from D0 to D. We define the strain along the horizontal axis as epsilon(x) as the equation. Considering the strain in the radical direction in this case, the strain is d minus d0 divided by d0. Here, d minus d0 represents the change in diameter. The ratio of d minus d0 to d0 is the strain along vertical axis epsilon y. We are more exploring about this equation later. But here, I would like to notify one thing. You should use capital letters of d for describing diameters to avoid confusions. Many textbooks use small character d to describe diameters, but d is often used elsewhere as an important symbol for a small fraction in differentiation and integration. You should have ever seen dt, for example. Many textbooks use small d and large d without clearly distinguishing them. This is very confusing. So, you should basically use large d for diameters and other values. The horizontal strain, epsilon y, is negative, when the vertical strain, epsilon x, is positive. When this value is positive, epsilon x is positive, then epsilon y should be negative. Once you imagine this process, it probably is not so difficult to understand. Then, Poisson's ratio is defined by the equation. This is the definition of Poisson ratio. In other words, it is the value of the horizontal strain divided by the vertical strain. It is the rate of slimming, which is how much the material has become slimmer. As I mentioned earlier, the signs of epsilon x and epsilon y are usually opposite. So, we will add a negative sign and call this ratio Poisson's ratio. If the Poisson's ratio is 0, it becomes a very simple story. Assuming that the material only stretches in the direction of the force applied and not deformed toward its orthogonal direction, the calculation becomes much easier. However, As you can see in the example of noodles, if you pull the material vertically, it naturally becomes slimmer in the horizontal direction. The material becomes slimmer when pulled. The Poisson's ratio varies between about 0.25 and 0.4, as shown in this table. For ferrous metals, generally, 0.3 is usually used. Softer metals, for example, gold and silver, are a bit larger. The same is true for plastics, such as epoxy and polycarbonate. So, let me now use the expression brittle. This is a property of materials, such as glass and ceramics. These materials crack when dropped. Materials that are highly brittle are known to have a relatively lower Poisson's ratio. You may remember the Poisson's ratio of glass or ceramic is somewhere around 0.2 or 0.25. Based on the definition, you need to add the sign of minus to the ratio of the vertical strain to the horizontal strain. Be noted that you should not use 0.3 for any kind of materials. For many materials, you can find the value on the catalogs of the material. If you can't find the value, you have to state the Poisson's ratio that you used. You need to be careful about this. Suppose the bar is extended and the volume is constant. The ratio of epsilon y to epsilon x, or Poisson's ratio, is 0.5. It may take some time to explain about this in detail. So, those who are interested in this point may consider why the Poisson's ratio would be 0.5 under the condition that the volume is constant.